Welcome everybody to this talk, Sputtering Targets by Powder Metallurgy for Display, Energy and Hardcoating applications. My name is Linke from Plansee, and together with my colleague Peter Polczyk, I have the pleasure to present you some of our interesting topics here at the SVC TechCon 2021. In the first part of this talk, I will give a short introduction to Plansee, to the company, and I will present two topics out of our current research, which is low resistivity MOSIN films for electronic applications, as well as some overview about molybdenum oxide sputtering targets for electronic and energy applications. The second part of this talk, sputtering targets for hardcoating, antibacterial and energy applications, will be given then by Peter. This year is actually a very important and special year for Plansee because 100 years ago our headquarters was founded in Reutte, Austria, nearby the lake, which is also named Plansee. Plansee High Performance Materials is a wholly owned division of the Plansee Group, and Plansee currently is active worldwide. Besides our, let's say, standard tungsten and molybdenum products, we are also producing different sizes and shapes of sputtering targets. We have planar sputtering targets, mainly used in LCD DFT or OLED production, and the size of these targets can become quite large. For rotary sputtering targets, we have also own production possibilities, and rotary sputtering targets can be used as monolithic targets or bonded targets. Some of the examples or applications is as back contacts in thin-film solar cells, but also for display applications. And of course, a very important and growing market is the microelectronic market, where we are also delivering molybdenum and tungsten disc targets for different wafer sizes. Within the materials that we are producing as sputtering targets, there's a wide range of different possibilities. As you can see here, mainly of course tungsten and molybdenum based materials are dominating all of our applications, like for display, thin-film photovoltaics, but also microelectronics. But we also see an increasing number of alloys or compound materials, not only for hard coating and triple applications, but those borides, silicides, but also carbides are a more and more interesting field of materials for different other applications. The first technical topic I want to talk about is about low resistivity MOSIN films for electronic applications. This approach, what we have chosen here to reduce the resistivity of the molybdenum thin films, is a quite important one, as for novel display applications, low resistivity gate lines are required, especially when it comes to high resolution or flexible OLED displays. If you could achieve it to have low resistivity gate lines within the thin film transistor structure, this would enable a lot of benefits, like higher conductivity if you want to, let's say, achieve a constant thin film thickness. But of course, you also could reduce the thin film thickness at a constant RS, which is in the other way important to reduce thin film stress, but which is also important to increase, for example, flexibility when you have banded substrate. And of course, you have a reduced line width at a constant RS. This idea of having low resistivity MOSIN films is not only important for display applications, it also could have benefits for other applications like back contact materials and thin film solar cells, but also a very increasing, let's say, application as electrodes in filters or MEMS applications. By depositing a tungsten seed layer, for example, under a sputtered molybdenum thin film, it is possible to have a reduction of nearly 30% in thin film resistivity. This is possible because this thin film seed layer, which can have a thickness of about 10 nanometers, for example, is strongly influencing the microstructure and domain size of the top molybdenum film, which results in a very strong increased conductivity of this molybdenum thin film. The idea of that approach has been described already about 20 years ago for tungsten titanium films for microelectronic applications, but here the first time it could be shown that it also worked for pure molybdenum thin films by applying such thin tungsten seed layers below the molybdenum layer. This effect can be increased even with increased temperature. So 30% reduction in resistivity is possible at room temperature. The same effect can be achieved but on lower absolute values when you increase the substrate temperature during deposition. On these graphs here, you see the influence of different substrate temperatures ranging from room temperature to nearly 200 degrees Celsius. And what you also can see is that the difference in the resistivity for all of those different substrate temperatures between a single layer Mo film and approach where you're using tungsten seed layer is more or less in the same range. So there's always a gain in about 30% resistivity possible when you are using the seed layer. Another group of materials I want to cover in my talk today are molybdenum oxides. Molybdenum oxides are a very special group of materials with a broad range of different properties depending on the oxygen content. On this graph here, you see some information, some general information on optical properties as well as on the electrical resistivity. For pure molybdenum on the left side, for example, the optical reflectivity is the highest and the electrical resistivity is very low due to the metallic character of this material. If you're increasing the oxygen content, you will get more and more properties from the oxide range, which are high electrical resistivity up to completely insulating for MoO3, and also the optical properties are changing a lot. For example, if you have a composition between MoO2 and MoO3, you can achieve it that the oxide thin films are highly absorbing, which is making them interesting for anti-reflective coatings. If you're going to the MoO3 stoichiometry, those thin films are highly transparent, for which other applications are interesting. Due to that broad range of different properties, these molybdenum oxide layers can be used in different applications. The dark oxide layers, for example, sputtered in a non-reactive process using molybdenum oxide ceramic sputtering targets, can be used as anti-reflective coatings for metal lines in high-end display applications. Also, electrochromic layers can be sputtered from this material, and molybdenum oxide are also an interesting material in solar absorbing layers. If you want to use transparent oxide layers, you can use reactive sputtering process, and those transparent oxide layers are interesting as hole injection layers for OLED devices, can be used as hole selective layers or back contacts for photovoltaic devices, and also as electrochromic layers. On the right chart here, you see some overview about the deposition rate for non-reactive and reactive sputtering process using a ceramic oxide sputtering target. These results already have been published a couple of years ago, also on SVC. For depositing thin films of molybdenum oxides, there are two possibilities. The one is reactive deposition, using a metallic molybdenum target or a ceramic molybdenum oxide target and adding oxygen content in the sputtering gas, which is quite interesting if you would change the stoichiometry of those thin films in a broader range, but maybe it's more difficult on large area as you really have to achieve a very good control of the oxygen distribution in the sputtering chamber. Another option is non-reactive deposition. Here you have the advantage that you do not have to add oxygen content or oxygen in the sputtering gas, but you have to use a ceramic molybdenum oxide. Those molybdenum oxide targets are currently available in different compositions with different oxygen contents. Our production process for producing such molybdenum oxide sputtering targets is based on powder metallurgy. That means we are using different oxide powders, maybe also adding metal powders, mix them, and are using hot temperature powder consolidation to achieve high density and good microstructure of that material. In general, for most of the applications, those consolidated targets are then also additionally machined and needs to be bonded, solder bonded on a backing plate. The microstructure of such a molybdenum oxide target material is depending on the oxygen content. Depending on the oxygen content, there are, let's say, different areas or fractional areas of oxide phases in the material, which makes it possible to tune the properties of those target materials depending on the oxygen content. So for example, electrical conductivity, thermal conductivity, but also fracture strengths of those materials are strongly depending on the oxygen content. And by using powder metallurgy, it is more or less possible to achieve the one or other properties depending on the final application. An important factor for using those molybdenum oxide thin films is the chemical stability. That chemical stability is depending on the oxygen content. And a very interesting thing is that you can improve that chemical stability for different water-based or non-water-based solutions by adding dopants into the molybdenum oxide. Those dopants can be, for example, other metals. It can be other oxides that you can mix or bring into the microstructure of that material. This can be measured in an electrochemical cell, and you clearly see here on this slide that by adding different dopants, the chemical stability explained by the corrosion current can be strongly improved for several molybdenum oxides. More results on this will be presented later that year on different conferences. More scientific information can be found in the technical program of the TechCon 2021, and together with our partners, we want to invite you to visit those poster and oral presentations. Now I want to hand over to Peter, who is explaining the second part of our presentation.
Hello everybody, my name is Peter Polczyk. Let us talk about targets for hardcoating, antibacterial and energy applications. The best way to deposit titanium nitride is sputtering in reactive nitrogen-containing plasma. Another possibility is to use ceramic titanium nitride targets in pure argon plasma. Let us study the idea of following experiment. In the work of Rainer Hahn from Vienna University, titanium boron nitride was deposited in the first trial using titanium and titanium diboride targets in reactive nitrogen-containing plasma. In the second experiment, the titanium boron nitride coating was deposited in pure argon using titanium, titanium diboride, and titanium nitride targets. Let us have a look to the diagram on the right side, showing the hardness as a function of boron content measured in the deposited coatings. The boron content was set by changing the power applied to the titanium diboride target. If we follow the magenta curve in the diagram, standing for the reactive sputtering mode, the hardness increases slightly up to a boron content of about 5% before it drops down with higher boron level. The reason is simply related to the increasing amount of boron-nitrogen bonds in the deposited coatings, which is good for low friction coefficient, but not so for hardness. Completely different behavior is shown in case of non-reactive sputtering, where the only source of nitrogen is the titanium nitride target. In this case, the hardness is increasing even to a level of 37 gigapascal for a boron content in the range of 8%. The message of these experiments is that it does matter where the nitrogen is coming from. The titanium nitride aluminum nitride target shown in the picture on the right side will maybe open some doors for new ideas. The next example is related to titanium carbide coatings deposited in non-reactive mode directly from ceramic titanium carbide targets, without any carbon-containing gases. In this work published by Michael Stüber, titanium carbide targets enriched with additional graphite powder were used for deposition of nanocrystalline titanium carbide particles in an amorphous carbon phase. By changing the ratio between titanium and carbon in the target itself, it was possible to deposit coatings with different values of friction coefficients. This is shown in the diagram on the left side. In the diagram on the right side, it is shown how the amount of carbon in the coating can be triggered by changing the bias for a constant target composition. The next possibility to work in non-reactive mode is related to the deposition of diborides for hard coating and wear-resistant applications. Our work related to the hot pressing technology makes it possible to manufacture big variety of diborides shown on the left side. Most of them are dedicated to sputtering, but some papers were published already for applications in arc evaporation. The question is, why to explore ternary diborides? I think these materials have big potential for certain applications as they show huge range of interesting properties. For instance, magnesium diboride is a superconductive material up to about 40 Kelvin. Rhenium diboride is known to be the most incompressible material. Titanium diboride is well known and established because of high hardness and not too bad thermal stability. Many researchers are working on these materials already, discovering new possibilities and maybe also new application fields. Related to very high temperatures applied in hot pressing technology, we would like to introduce new products described by the name metal-doped graphite. Some examples of arc evaporation cathodes, as well as targets for laser arc evaporation technology, are shown in the pictures. As we use very small size of metal particles, we can achieve a very homogeneous distribution of these particles in graphite matrix, shown on the left side. What are the applications? From today's point of view, these are high hardness TAC coatings, metal doped DLC with still very low friction coefficient but increased thermal stability, and also thin films for fuel cell interconnector coatings. The next case I would like to talk about is related to nitride-based decorative coatings. In order to screen the big variety of possibilities in one experiment, it seems to be useful to work with a combinatorial approach, shown as a target on the left side. In this case, we applied titanium kappa target in combination with pure zirconium target to screen the whole titanium kappa zirconium system. In front of such a target, several substrate samples were placed. If you look to the diagram on the right side, you can follow the decrease of L value, these are the gray dots, with increased kappa content in the coating. At the same time, A value, standing for red, is increasing and the blue B value is decreasing. A very simple approach supported by application of powder metallurgical produced targets. The next and last example is also related to powder metallurgical production of targets with flexible compositions. In the last few months, we have been facing strong demand on targets containing small amounts of copper or silver. These elements are well known for antibacterial behavior. The direct alloying of targets with these elements seems to be the simplest way for deposition of antibacterial surfaces. In this case, you are not forced to work with co-sputtering. You can guarantee a uniform coating composition, and you can work in your PVD system with high deposition rate. In the most cases, such coatings are deposited in a reactive mode for nitrides, having not only high wear resistance, but also being active against bacteria.
At the end of this talk, we want to thank you for listening to our presentation and to our topics. For further discussions, feel free to contact Peter or me by email or phone. Thank you and take care.